Okay, so let's move on to measurements. Okay, so we are going to use in this class and in any science class, you should be using the SI units. SI stands for System International. It's the French. The French are kind of the ones that started standardizing everything. We know this more as the metric system. The metric system is the standard set of units. Standard set of units. For science. And really, it should be everywhere. But certainly for science, we have to use the same standard set of units. We can't use different units here in the US that they do in Europe, for example, because then we'll have to do conversions, then it's really annoying to do that. So the premise behind this is we have a bunch of base units, very simple standard measurements. So if I wanted to measure something, if I wanted to measure the mass of something, I'm going to use the kilogram. And that's how we're going to do it. Everybody is going to use mass. Very simple measurement. We're going to use kilograms. Okay. So if I want to mass something, weigh something, I simply use the mass in kilograms. Very basic measurement, right? How much gravity is pulling on something, how much mass is present. If I want to measure a distance, I'm going to be using the meters. Okay. And we're going to change these by adding prefixes and changing things, but length, a very basic thing. How from here to here, we've got it. Time is going to be measured in seconds, in minutes, and hours, and years, and so on. But time is measured in seconds, and we know the conversions there. Temperature. Temperature is going to be measured in Kelvin. Maybe you've not heard of Kelvin yet, but it's almost the same scale as degrees Celsius. We're not going to use Fahrenheit. We're going to discuss these individually, but temperature, it's how much energy is present, how fast molecules are moving, but we don't really care about that. Temperature is temperature, and we're going to measure it in Kelvin. The amount of substance, if I counted the number of molecules present, which is impossible to do because there are so many, the amount of a substance, we are going to measure in moles. So we have these very basic things. Mass, how much matter is present. Kilograms, perfect. Very basic measurement. Length, distance from here to here, perfect. Time, temperature, the number of things present, the amount of substance, we're going to use moles. These are our base units. And what turns out is we can actually make more complex units by using these base units. So these are like the atoms of the unit world. Okay, so we're going to use these and we're going to expand upon them to get a bunch of other stuff. And we're going to see that when we get to what we call derived units. So these are our base units. You should know these. They're going to be kind of come second nature to you, but it's going to be important that you know them. Prefixes. The way the metric system works is we know that we have the gram, the meter, the second, the Kelvin, all of these things in terms of, okay, what am I measuring? Distance, mass, time, those types of things. But if I'm taking a very small measurement, I can use prefixes to decrease the size of it. So the numbers are reasonable, right? I am not going to measure the size of an atom by saying, oh, it is actually 0.0000000000014 meters, right? That's ridiculous to do it that way. So instead, we're going to say, oh, the length of that bond is 1.5 picometers or 15 picometers, right? So pico is a very small, there are 1 picogram, or in this case, is a very, very small amount. So what we do is we use these prefixes to make the numbers reasonable. That's why we use a prefix, right? I'm not going to measure the distance from me traveling all the way to wherever you are in meters, because that's probably a huge number, right? We're going to use it in kilometers, right? Or we're going to use it in kilometers, right? I'm going to have it's 1,001 kilometer is equal to 1,000 miles. So instead of me saying, I don't know, 200,000 meters, I'm just going to say, oh, I'm 200 kilometers from that location, right? So the number is more reasonable by doing that. So there are prefixes that increase the base unit, and we are going to focus on the kilo. That's really the one we're going to use the most. Mega, giga, tera. Those are important to, I mean, it's important to know, but for the most part, a kilo is the largest we're going to get in science and chemistry. So kilo is a lowercase k. So if I want to measure something in kilometers, I'm going to put that little k before I'm going to put that little K before the meter. So 1 kilometer or kilometer is equivalent to 1,000 individual base units, 1,000 meters. Okay, so 1 kilometer equals 1,000 meters, or 10 to the third. 10, 1 with, and again, remember this number here is just the number of zeros you tack onto 1. 1 plus 3 zeros. That's how we would do it. Okay. There are also prefixes which make things smaller. Okay, so we have the deci, centi, milli, micro, nano, pico, femto. So really get really tiny here, right? So centi, we're going to use centi, we're going to use milli, we're going to use micro, we're going to use nano. Those are the ones we're going to use most. Pico is used when we're talking about atoms, so I guess I'll throw that in there as well. But these are the ones that we're going to use the most. We use small units because we're dealing with a small world. So centi. Well, let's start with deci. Deci, 10 raised to the -1. I like looking at the opposite example because I don't want to deal with negative numbers. 1 meter is equivalent to 10 decimeters. And when I ask this, I often ask my students to think about, when you see deci, how many years in a decade, right? Deci, decade, 10. 10 years in a decade. There we go. 10 years in a decade, 10 decimeters in 1 base meter, right? How about centi? How many years in a century? Well, 100. And that's where the 100 for the centi, 100 centimeters in a meter. How many years in a millennium, milli? 1,000. There's 1,000 millimeters in 1 meter. So again, we see this, we're used to doing those measurements, centi, milli. And then once we get below milli, so now what we're going to notice is these things jump by 3, jump by 3, jump by 3, jump by 3. Okay, so 10 to the third, 10 to the sixth. This right here is 10 to the third, 10 to the sixth, 10 to the ninth, 10 to the 12th, 10 to the 15th. So times 3, times 3. I shouldn't say 3. I should say increases by 1,000. That's more appropriate. Yeah, so it increases that by 1,000. So 1,000 times, 1,000 times, 1,000 times. But notice that it just jumps by 3. Okay, so by putting a nano, an n in front of the meter, we're saying really small. It's 1 nanometer is equivalent to 10 to the 1 nanometer is equivalent to 10 to the -9th meters, or 1 meter is equivalent to 10 to the 9th nanometer. So we're going to come back to this, but we are going to use these examples to do a bunch of conversions. And the opposite one is easier for me because it's just, you don't have to deal with negatives and life is easier that way. All right. Temperature. So we looked at the prefixes, we looked at the base units, then we looked at the prefixes. So we can increase and decrease to keep our numbers normal, right? And so let's take a look at temperature. I'm going to fix something quickly. I keep forgetting to fix this. The human body temperature, this is the stuff that we know. Fahrenheit, human body is 98.6 degrees. Fine. Room temperature is about 75 or 70, I think. Freezing point of water, what is it in Fahrenheit? 32 degrees Fahrenheit, and I don't know what absolute zero is, but these are important. I'm never going to ask you to use Fahrenheit because Fahrenheit is just a very strange scale. Okay, so we are going to ignore Fahrenheit and we're going to look at Celsius and Kelvin. Those are the two that we're going to focus on. These two, Celsius and Kelvin. So we're going to focus on this, and I think these numbers are off a little bit too. Let's fix them. 373, that is correct. Human body temperature, I don't know if that's right. Room temperature, oh, room temperature 77. Room temperature is 20. Well, I'm not going to worry about those numbers. We're just going to do the math. So freezing point is -2. Oh, that's Kelvin. All right. I'm not going to worry about that because there's a handful of different important stuff that we need to focus on. So this is what happens when you copy something from the internet. All right. What I know, 1 degree Celsius equals 1 Kelvin. They're the same scale. They're just offset. Okay. So I'm going to ignore all of this, and I'm just going to simply say, okay, if I've got a thermometer, I've got degree C on this side, Kelvin on this side. That'll work. 0 degrees Celsius is going to be 273 Kelvin. This is the freezing point of water. Okay. Up at 100 degrees Celsius, because they're offset, 1 degree Celsius equals 1 degree Kelvin. So this is the boiling point of water. The Celsius scale is based on the freezing point of water. That's the 0 point. Okay. Differently, a little division here, the freezing point, or the negative 273 degrees Celsius, that's a 3, is equal to 0 degrees Kelvin. This is what's known as absolute 0. There is nothing colder than absolute 0. It's impossible. In fact, the universe is actually, like, out in space, deep space, is 3 Kelvin. So there's actually, it's warmer than absolute 0. Absolute 0 means there is no motion at all. All molecules, all atoms are locked into place. They're not moving at all. There's not even a wiggle. They're not moving. We've gotten very close. We're like 0.0001 Kelvin. We've gotten very close to absolute 0, which is wild. Okay. But the point being is the gap from 0, that gap is 100 degrees Celsius. The gap here is 100 degrees Kelvin. So they're just on a shifting scale. So what that means is when we're doing the math for these things, we are just simply going to add or subtract 273. Okay, so let's deal with the first part here. Conversions from Celsius to Fahrenheit, there's your formula. Celsius times 1.8 plus 32. Never going to use that, right? By the way, the easy way to do it is just to double the Celsius and add 30, and you get a close ballpark. So if you're ever in a situation where you have Celsius and you want to know in Fahrenheit, double it, add 30, and you're about good. So we can rearrange this. Hopefully you understand how to rearrange these things, and we're going to talk more about this type of math. But moving this around, you're going to end up with Fahrenheit minus 32, because I move over the 32 first, and then I'm going to divide by 1.8, right? So I move this over first, and then divide by that to get my Fahrenheit. But I don't care about any of this. All right. Certainly, it's important to know that. I'm going to ask you relativistically. So if I'm going to say something like, "Hey, what's the highest temperature?" And I will give you a bunch of temperatures, and you have to recognize where Fahrenheit is on that scale, right? Is it above boiling water? Is it below boiling water? So just know that, again, Fahrenheit, 212 degrees Fahrenheit is boiling point of water, and 32 degrees Fahrenheit is the freezing point of water. Easy to remember that up here in the north, because we judge the temperature and when the roads are going to freeze. But conversions between degrees, remember, it's the same scale. 1 degree Celsius equals 1 Kelvin. So that means that we're offset. By the way, you don't really have to worry about this 0.15. That's the proper way to do it, but 273 is just sufficient. So Kelvin to Celsius minus 273 to get to Kelvin, plus 273 to get to Kelvin, minus 273 to get to Celsius. Okay, so the important part here is the Kelvin number will always be higher, larger, higher than the degrees C. Okay, so what that means to you is just simply, after you do this calculation, after you look at this, recognize that if your Kelvin is higher than the degrees C, you've done something wrong and you have to go the other way. Okay, so 273, that's the magic number. Great. All right, so let's continue on and look. So we've looked at our base units: mass, length, time, temperature, and the amount of substance. We're going to now derive units. We're going to use these atoms, the form of these base units, and we're going to do math on them. So what we can do is we can come up with these new derived units. So we can come up with a new physical measurement by combining, by doing math, on base units. So let's take a look at that. So these are the base units. We measure distance. But how about area? If I asked you, hey, what's the area of the room you're in? You would always say, well, it's always going to be length times width, right? That's going to be the area of the floor. So length times width, that is my area. Well, how do we measure length and how do we measure width? Well, length in the base unit is going to be measured in meters and width is going to be measured in meters. What is a meter times a meter? It is going to be meters squared. There is my derived unit. So whenever you see meters squared, distance squared, you now have an area. So we've taken a base unit, we've done some math, we've multiplied it by itself to come up with the area, right? So we use these base units in order to figure out, ultimately, these new derived units. So we have a new type of measurement. Hey, I can measure the area of something by just simply taking two distances, right? How about volume? Again, going back to these base units, volume is measured by length times width times, so there's the area, times height. So if I take the height of the room, I'm going to get the volume of the container or volume of the room that I'm in. So again, length is in meters, like I said, width is in meters, and then I'm going to multiply that by the height. So altogether, that is meters cubed. So we now have these cubed units are going to give us a volume. Okay, again, just the base units. And so now we start to see this. So now we start to use these base units to come up with new things. So acceleration, if you're in your car and you're accelerating or you drop something and it's accelerating because of gravity, acceleration is measured by the distance something travels. And we know distance is going to be measured in meters divided by time. And we see that time, the base unit for time is seconds, but we have to square that. So meters per second squared. There we go. We now have a derived unit for acceleration. How about velocity? Well, if you're traveling in your car, how much distance over time are you traveling? So meters over the amount of time, seconds, meters is the distance measurement for the base unit, and time is in seconds. So meters per second. So meters per second is going to be my velocity measurement. So you're starting to hopefully understand this. How about force? Well, force is going to combine a base unit in mass times acceleration. Acceleration, which we just did, is meters over seconds squared. So now let's multiply meters times meters gives me meters squared, all divided by seconds squared. There we go. There is my derived unit for force. Well, it turns out if you want to do work on something, it is just simply force, which we just had, meters squared over seconds squared times distance. Distance is meters is, well, force. Oh, I'm sorry. Am I skipping one? Oh, mass. Yep. Sorry. I'm going to back up. It's not meters. Whew, safe. That's my fault. Mass is measured in kilograms. Sorry about that. Acceleration is measured in meters per second. So the top is kilograms times meters. Okay, better. So kilograms times meters per second squared. Okay, so we have a force measurement. Well, work is me taking an object and moving it. So I have my cup here and me moving it. It weighs something by moving an object. That is me doing work on that object. So the force it takes me over the distance I traveled. So force was measured in kilograms times meters over seconds squared times the distance in which I traveled, which is meters. So together, kilograms times meters squared all over seconds squared. There we go. There is my work. Okay. Again, we're using base units and now we're adding in more derived units, which came from those base units to create this new stuff. How about pressure? Force over unit area. So we know force, again, is one we just came up with, or the one we had, kilograms times meters over seconds squared, all divided by area. And we know area is meters squared. Remember, when we're doing this division, just to bring you back to math, right? We're always going to take The top one, we're going to skip this term. You might have something different. This is what they had when I was in school. We're going to skip this term. By that, I mean, we're just going to rewrite that term. So if I skip the top, I'm just going to rewrite kilograms times meters all over seconds squared. We're going to flip this from multiplication, division to multiplication. So instead of, I'm going to multiply that out. Oh, sorry, skip. Flip is going to be the last one. We are going to skip switch. I'm going to switch the sign from switch is I'm going to go from division to multiplication. And then I'm going to flip the bottom. I'm going to flip the bottom. So meters squared, which is really meters squared over 1, I'm going to put 1 over meters squared. And now I can do math on this. Meters cancels out the meter squared, leaving behind meters. So kilograms on top, all over second squared times meters. There we go. Skip, switch, flip. And we have our pressure, kilograms per meter second squared, right? We did velocity. How about energy? Energy is measured in mass, which is kilograms, got it right this time, times velocity, which is meters squared over seconds. Oh, velocity meters, oh, because it's squared. The whole thing is squared. So that comes out to be kilograms times meters squared all over second squared. There you go. You have energy. Okay. By the way, notice that energy is the same thing as work because they are the same thing, as it turns out. But anyway, that's a derived unit. The idea that you can take those base units and you can just say, all right, well, distance, time, you know, whatever you want to do. All right. So let's take a look at some derived units we use a lot. Density is a derived unit. Density is going to be measured as mass per unit volume. Mass is measured in kilograms. Volume is measured in liters. Oh, sorry, let's talk about volume. We know volume is measured in those cubed units. So meters cubed, okay? Well, it turns out we can actually change these volumes. Instead of using the cubed units, we can convert them into liters, okay? And so these are going to be somewhat important to know, but this is the really important 1 milliliter is equivalent to 1 centimeter cubed, okay? And 1 liter is equivalent to 1 decimeter cubed, which is not as, this is the one that seems to be more relevant. This is the one you're going to use more often. 1 milliliter equals 1 centimeter cubed, okay? Great. So with that in mind, mass per unit volume, that means that our densities are going to be measured in some amount of mass, and we typically look at grams per centimeter cubed or grams per milliliter. In fact, I probably should say solids are typically measured in grams per centimeter cubed because solids are regular most of the time or a good portion of the time, so we use the cubed units. Liquids are measured in grams per milliliter or grams per volume. Gases are usually measured in grams per liter. Okay, so the unit does change typically based on the stuff. And here we have densities all with the same unit, and you can see those values. A density is going to, so if I have a container, there's my unit volume. Okay, so if I have 2 densities here, or 2 cubes that are the same size, let's pretend I'm good at drawing and those are the same size. Let's put 3 objects in here. 1, 2, 3, 4, 5, 6, 7. This has, if they're the same volume, this one has more mass equals increase in density, right? There's more stuff in the same space. That one is more dense because it has more stuff in it, okay? Yeah, good. All right. Units of energy, we're going to get into this when we get into the energy chapter. 1 joule, we're going to use joules and we're going to use calories. There's the conversion between joules and calories. By the way, 1 kilocalorie, which is equivalent to 1,000 calories, right? That kilo is going to give you that. Weirdly enough, as a quick aside, you don't need to know this, but 1 kilocalorie is equivalent to 1 calorie. They use, for some reason, maybe because we hate the metric system so much, if you look on the back of a food container, a C is a kilocalorie, as it turns out. So yeah, so these are the units that we're going to use. All right. So uncertainty in measurement. So this is I think we're going to, yeah, uncertainty in measurement. So we've talked about units, and I'm going to leave it here. We're going to get into measurements and the number side of things. So we were looking at the individual units, and we're going to come back to the units in a little bit, but we are going to take a look at measurements in the next one. So that was units. That's one portion of the answer, and then the number is the other part. So anytime you write a number, and this is going to be really important, anytime you write a value, you must have a number with it, you must have a unit. So those two things have to go hand in hand, or you need both to make the answer correct. So we'll start there. We'll stop here, and we're going to pick up with measurements in the next video.